Welcome to this introductory lecture on causal inference in econometrics. There are some big words in the title of this lecture that maybe deserve explanation. In particular, I want to explain what causal inference means. Causal means that we're interested in causality. That is, we believe that in our society, in the economic environment that we live in, there are relationships of cause and effect. By identifying the causes and by manipulating them, we as politicians, managers, or citizens can affect change and move our society in a different direction, in a more preferable direction, hopefully. Inference means that we want to learn about these causal relationships using data. Of course, learning from data is nothing special. That's what we as humans do all the time. Every ray of light that enters your retina is data that you use to interpret the world around you, that you use to learn about the world around you. What is different in what we're going to accomplish here is that we will learn from the data using rigorous statistical methods from the toolbox of econometrics. And they will be rigorous in two important ways. First, we will be very explicit about the assumptions that we make about the underlying structure of reality. Or the world model, if you will. Whenever we are interpreting data, we are assuming some underlying structure that we a priori assume to be true. That's what we call a model. For example, if you are seeing a person and then you turn around 360 degrees and you see a person now that looks exactly the same as the person you just saw, then you assume that it's the same person. The model that you use to interpret the data that you're perceiving incorporates the assumption of object permanence. When we are interpreting data naively, the model that we're using to interpret the data is often very implicit, and we will probably be hard-pressed to define exactly what it is. Econometrics is different. We will always be very deliberate in our choice of model, and we will always explicitly state the assumptions that the model makes about the structure of reality. This will be very helpful for identifying the limits and weaknesses of a data analysis. The second dimension, along which we will be very rigorous, is statistical error control. Statistical error control keeps us from overgeneralizing patterns that we see in our data. When we look at a small number of data points, and that's what we typically do, it's perfectly possible that there are patterns that seem to suggest a causal relationship that doesn't really exist. These patterns can randomly occur through our choice of data points that we're looking at, and they wouldn't persist in a different choice of data sample. To give an example of a causal relationship, consider the effect of classroom size on student learning. Now you may be wondering, why are economists interested in education? Well, we as economists consider education as knowledge production. Education uses scarce resources such as teacher time or study materials to produce knowledge. Many parents and policymakers believe that there's a causal relationship between classroom size and student learning. Specifically, they believe that smaller classes lead to better learning outcomes for students. Presumably because in a smaller classroom, the teacher has more time to focus on the individual student. Let's picture a classroom at a middle school. We have our teacher, and we have a bunch of students. If there are only a few students, then this is a small classroom. If there are many students, then this is a large classroom. To explain how economists think about causal relationships, we have to introduce three important concepts, two of which are very obvious, so we start with the less obvious one. And this one addresses the question of where we are measuring the causal effect. So we're asking, who is affected? For our example here, there are different choices that would work. For example, we could say it is the individual student that is affected, and we're measuring everything at the student level. Well, here we're making a different choice. We're measuring everything at the classroom level. In econometric language, we say the classroom is our unit of observation. Now we get to the two obvious concepts when we talk about causal relationship. The first corresponds to the question, what is the cause? And the second one corresponds to the question, what is caused? What is the cause in our example? That's right, it's classroom size. The fancy econometric word for cause is treatment. This term is derived from the medical literature, where we try to use data to evaluate the efficacy of a medical treatment. For economists, a treatment doesn't have to be a medical treatment. It can be anything that can be manipulated. If it's something that cannot be manipulated, then, as you'll see in a second, we will run into some philosophical issues of defining just what a causal effect is. More pragmatically, why would we be interested in learning the effect of something that we can never change anyway? What is cause in our example? Yes, it's student learning. Let's say student learning is reflected by test scores. Economists call the variable that is affected by the cause the outcome. As you will notice repeatedly throughout this class, economists are very lazy. Often, instead of using complicated words, we like to use simple symbols. So instead of talking about classroom size or using the more general term treatment, we will simply use the symbol capital D. And instead of referring to a test score or the outcome, we simply use the symbol capital Y. These symbols give us a really compact way of representing the causal relationship using a causal diagram. In a causal diagram, we use arrows to represent causal relationships. In our case, we believe that D affects Y. The arrow here represents the causal effect that the treatment has on the outcome. We haven't defined exactly what a causal effect is, and it is the most exciting concept that we cover today. In fact, everything I've done so far was just building towards being able to explain what the causal effect is. In the following, I want you to think of this classroom as a real classroom that exists somewhere in the world. Since it's a real classroom, it is observable, and I know what its classroom size is and what its test score is. I've only drawn a few students here. Let's assume that there are more than 3 students in this class. Let's assume that there are 35 students in the class. And let's say that the test score is 66. To emphasize that this could be a real-world classroom, I've picked the classroom characteristics from a real-world data set. This data is from a famous research paper by authors Engrist and Levy. I've plotted their data, class size against test score. Every point here represents an observed classroom. And look, here's our classroom. It sits right here. It has a class size of 35 and a test score of 66. These are exactly the numbers that I gave here. Suppose that we are able to manipulate classroom size for this classroom. This means we can take this classroom and put an exact copy of this classroom down here. Then we pick a new student, little Jimmy, down here. And we move Jimmy into the class. So now there will be 36 students. This is the only change we make in this classroom. Everything else we keep equal. The Latin term for everything else equal is ceteris paribus. This is a term that we will use a lot. We imagine this hypothetical classroom in order to define a causal effect. It doesn't actually factually exist. We call it the counterfactual classroom. It is tempting to call the real classroom the factual classroom, but no one ever does that. What are the characteristics of the counterfactual classroom? Well, it has a class size of 36. Now, I don't want to write D for the class size here, because I want to reserve capital letters for variables that represent real values, not hypothetical ones. So instead I write lowercase d equal to 36. What is the outcome for the counterfactual classroom? Our hypothesized causal relationship suggests that the outcome should depend on the treatment. Let's make this explicit by writing y as a function of treatment. The treatment lowercase d can be any value that represents a valid classroom size. Therefore, y of lowercase d represents hypothetical outcomes under a certain assigned classroom size. In particular, if we put in the real observed classroom size, we'll get the observed outcome. The y as a function of an hypothetical treatment is called a potential outcome. The outcome under the counterfactual is therefore the potential outcome at a classroom size of 36. Since this number only ever becomes relevant in a hypothetical scenario, we don't know what it is. If it is true that smaller classrooms are good for student learning, then this number should be smaller than 66, maybe 65? But we don't even know if that conjecture is correct. So for all we know, this could also be 70. Well, we don't know what it is. Regardless of what this number is, at least now we have all the tools that we need for a clean definition of the treatment effect. The treatment effect is equal to the outcome in the counterfactual scenario. This is the outcome where we have added one student to the class size, minus the outcome in the observed scenario, that is the outcome where class size is equal to capital D. In other words, we define the treatment effect as a simple before-after comparison, except that the after never really happens. It only happens in our head, in our thought experiment, where we consider the counterfactual. In our example, this here works out to be potential outcome at 36 minus, we don't have to speculate about the observed outcome, it's 66. The ceteris paribus treatment effect that we've defined here is the causal effect that we're interested in. So now we've explained what causality means to us, we can move on to inference. How can we learn the value of this treatment effect? Clearly, since we know the observed outcome, the difficult part is figuring out the counterfactual outcome. This is called the identification problem. Recall our purple classroom from before. It has a class size of 35 students. To figure out the treatment effect, we have to consider the counterfactual of a classroom size of 36 students. I said previously that we don't observe a counterfactual outcome. Let's think a little bit about why that is true. Why can't we just change the classroom size from 35 to 36 and then observe our counterfactual outcome? Well, first off, we as researchers usually don't have the ability to change the classroom size. That decision is up to the school principal, the school board, politicians, or whoever decides on classroom size. It's usually not researchers. But suppose that we have this extraordinary power. We can just change the classroom size any way we want. It's still not really enough. Why is that? Well, we haven't really talked about what our outcome is. We said test score. Let's be a little bit more specific. Let's say this test score at the end of grade 7. So we are looking at learning outcome during grade 7, right? That makes sense. So we've observed that for this class. Now let's change the class size to 36. Let's suppose we're able to do that. How do we get the test score from grade 7? The students have already done grade 7 once. Well, suppose we have the power to make them take grade 7 again, so that we can observe a new learning outcome for grade 7, a second learning outcome. The problem is that the learning outcome for a classroom size of 36 is not recorded under ceteris paribus circumstances. We have changed a lot of things in addition to classroom size. For example, since the students have already taken grade 7 before, they've already studied a lot of the topics, so they have entered grade 7 with a different set of prior knowledge. Also, all the students are older and more mature. As you can see, we've changed all of these things in addition to changing classroom size. This is not what ceteris paribus means. The only way that I can think of to really record the ceteris paribus counterfactual outcome is if we have time travel. After the students have taken grade 7 the first time around and we've recorded their baseline learning outcome, we travel back in time, wipe their memories, and make them retake grade 7. At the end of the year, we record the counterfactual learning outcome. Yeah, that's the only plan I have, and it's not really feasible because I haven't really figured out time travel. No good news on that front. I hope that you're convinced now that we can't observe the counterfactual outcome. Let's focus on things that we can actually observe. For this classroom, we don't observe a class size of 36. But there may be a different classroom where we actually have a class size of 36. Let's say this is the green classroom. It also has lots of students, has a teacher, a different teacher obviously. And this class has little Jimmy in it. It has a class size of 36. Recall that class size is our treatment. So this classroom receives more treatment than this classroom. We say it receives higher treatment intensity. So this is the high treatment intensity classroom, and this is the low treatment intensity classroom. In a lot of treatment effect settings in medicine, for example, treatment is binary. That means you either get the full treatment or you don't get any treatment at all. For example, you would be in the high intensity group if you get all 3 doses of a 3-dose vaccine, and you would be in the low treatment intensity group if you don't get the vaccine at all. In such a setting, we say that a high treatment intensity unit is treated, and that a low treatment intensity unit is a control unit. Let's use these terms also here. For both of these classrooms, we observe learning outcomes. So how do we get at the treatment effect? A natural approach is to subtract the control outcome from the treated outcome. This is not exactly equal to the definition of the cause effect, so we shouldn't put an equal sign here. We just want to indicate that this is a guess based on our data of the treatment effect. A guess based on data is called an estimate. To indicate that a value depends on data, we often put a hat on it. To check whether this is really estimating the treatment effect, let's make it look a little more like our definition of the treatment effect. That is, let's make it look more like this. The treated outcome is the potential outcome at a class size of 36. The control outcome is the potential outcome at a class size of 35. 36 is equal to the baseline class size plus 1. And 35 obviously is just equal to the baseline class size. Now does this look like this? Almost, but not quite. Can you see what's gone wrong? Yes, exactly. Here we have the potential outcome function for the green class and not for the purple class. the potential outcome functions don't necessarily have to be the same. To explain why, let's think more carefully about the economic environment that we are studying. And let's do this using a causal diagram. We are studying test scores. This is our outcome variable. We're interested in the effect of class size. This is our treatment. Our conjecture is that there is a causal relationship between these two, and we indicate the causal relationship by an arrow. Clearly, class size is not the only factor that has an effect on test score. Consider, for example, the socioeconomic background of the students in the classroom. For example, you may imagine that a student who has highly educated parents is more likely than other students to receive help with homework. We expect socioeconomic background to also have a causal effect on the test score. Socioeconomic background has many facets. In the data that I showed you earlier, it is measured by a variable called PD index. This stands for percentage disadvantaged and gives the percentage of disadvantaged students where disadvantaged is defined by several characteristics of the parents. The composition of socioeconomic backgrounds in the classroom is obviously determined by the neighborhood that the school is in. Neighborhood may also affect class size. For example, if the school is located in a rural, sparsely populated area, there may be only a few students entering school each year, only enough students to have one small class. So neighborhood can affect the size of the student cohort, which in turn affects class size. The PD index is also observed by politicians who may use it, and actually do use it, to allocate more resources to schools with a high percentage of disadvantaged students. For example, they may have smaller classes in such areas. I hope that I've convinced you that small classrooms and large classrooms may be very different in terms of student composition, and that these students may react very differently to differently sized classrooms. Therefore, we shouldn't expect all classrooms to share the same potential outcome function. There may be systematic differences in potential outcome functions, or unsystematic ones. Let's start with the systematic ones. Assume that smaller classes tend to face a different PD index than larger classes. We've already discussed that the PD index has a connection to the kind of potential outcome function that we're assuming. This creates a systematic relationship between the class size that we are seeing and the kind of potential outcome function that we should be expecting. A variable like PD index that is lurking in the background and is systematically changing the potential outcome functions is called a confounder. If we observe this confounder, then we should be able to deal with it by just slightly changing the potential outcome framework. Let's quickly recap the variables that we observe. We observe treatment D. This is class size. And we observe outcome Y. This is the test score. Now we've added a new observable variable, the PD index. And this is the confounder in our example. And we abbreviate it by the symbol X. The potential outcome defines what the outcome will be under a hypothetical treatment assignment of small d. So this is a classroom size that's potentially different from the observed classroom size. For every possible treatment intensity, we assign a potential outcome. We previously called this y of d. Now we've added the confounder x, and we treat x similar to d. That is, we're thinking about different levels of x that are conceivable. Confounder level lowercase x. We argued that the confounder should have an impact on the potential outcome. This is not apparent in this notation, so let's change that. And we're letting the potential outcome depend on d as well as x. There you go, that wasn't too hard. Now we've incorporated confounders in the potential outcome framework. Recall our purple classroom. It was our baseline or control classroom. It has a classroom size of 35. It has to have a value of the PD index. Let's just say that is 20. And it has an outcome, which is the potential outcome evaluated at 35 classroom size and 20 PD index. The blue classroom was our treated classroom. It had one more student. It certainly has a PD value. Let's just say 35, and an outcome of the potential outcome evaluated at 36 and 35. Now we see clearly when we're comparing the two, we're not just comparing different classroom sizes, we are also comparing different PD indices. That's no good. From this comparison, we don't expect to learn much about the pure effect of a larger classroom. But don't despair, this seems easy to fix. We've just chosen the wrong blue classroom. Recall that the blue classroom was supposed to be a stand-in for the counterfactual purple classroom that we don't observe. But the counterfactual purple classroom is a ceteris paribus classroom where the x shouldn't be changed. But here actually we see different x's. So why don't we choose a blue classroom that has the same x as the purple classroom? There we go. This is already looking much better. Now our treatment effect estimate is treated y minus control y. So it's equal to potential outcome y at 36, 20 minus potential outcome at 35, 20. And we can rewrite this as before. And key is, of course, that now here we have the same x. Let's try to implement this strategy for estimating the treatment effect using our data. Here I've plotted our data, this time against the dimensions of percent disadvantaged. So this is our confounder. And class size, this is our treatment. Here's our example classroom. It's still here, going strong. And now we're looking for potential in-sample counterfactuals. So our classroom has a class size of 35. So we want to look at classrooms that have a class size of 36. So all of these. Also, they should have a similar percentage disadvantaged. So I'm looking in this range. This gives us candidates for the blue classroom that are located here. That's great. If everything works out as we anticipate, we should be able to choose any of these classrooms and then just use their y as the blue y. And then we can estimate the treatment effect, where we are controlling for the effect of the compounder. So let's zoom in on these classrooms. I have them all here. They have percentage disadvantage between 17 and 23. They all have a classroom size of 36. Here's our classroom for comparison. Now here, those are the test scores, and oh no, there's a problem. They all have different test scores. Even those that have exactly the same percentage disadvantaged have different test scores. So what should we choose as the blue y. Our choice will have huge consequences. If we choose one of these, for example, we will estimate a positive treatment effect. If we choose one of these, we will estimate a negative treatment effect. How do we make the right choice? One thing that we have definitely learned is that treatment and confounder don't fully determine the outcome. There are other things that matter and that shift around the potential outcomes. Now, this could be an additional confounder that we haven't taken into considerations. But I want to propose something else. You remember when I said there are systematic and unsystematic differences in potential outcomes? Well, the confounder caused differences were the systematic ones. Now, let's look at the unsystematic ones. To talk about unsystematic differences, we have to recall a very old concept from statistics, the concept of an error term. We are now about to impose some restrictions on how we think test scores are produced. That is, we're going to make some model assumptions. As I promised you before, whenever we make assumptions, we are very explicit about that. Oh yeah, now I see. This was supposed to be word model. We're making model assumptions. Let me just fix that real quick. Here we go. So what kind of assumptions are we imposing? As before, we assume that outcome is given by the potential outcome evaluated at the observed treatment and observed confounder. This in itself is not restrictive at all. But now we're going to make some additional assumptions. We assume that this is equal to some function m of treatment and confounder. And this function is the same for all classrooms, plus an error term u. Once we assume that this part is the same for all classrooms, you see immediately that we need an additional component to explain that all of these here don't have the same test score. In our new model of test score production, these differences are explained by these classrooms having different error terms. Let's just note that u is our error term. And the idea of an error term is that it is completely unsystematic. Statisticians say it is random noise. So for some classrooms this will be positive, for others it will be negative. And if we average over classrooms, then the average will be close to 0. This gives us a completely new idea for choosing the blue classroom. The blue classroom shouldn't correspond to any individual classroom. It should be an average of appropriate comparison classrooms. In the average, the effect of the error term will wash out. For example, we could average over all of these classrooms. They seem to be good comparison classrooms. In preparation for defining the average, let's label them. Let's call this the I equal 1 classroom, the I equal 2 classroom, I equal 3 classroom, and so on. To identify values corresponding to a classroom, we give all values an I subscript. For example, we would denote the test score in the first classroom here as y subscript 1. We're counting 1, 2, 3, 4, 5 candidates for the blue classroom. Let's write this as blue n equal 5. Now we have enough notation to describe our idea that the average error term is 0. To formally write down the average over the error terms, we sum over all of the 5 classrooms, starting with the first classroom up to the 5th classroom, right? This was our blue n. We sum the error terms, and now we divide by the number of classrooms, blue n. We are hoping that this will be approximately equal to 0. Before we move on, I have to correct some unfortunate notation. I chose blue here as a color for the error term, but this is not meant to indicate that the error term is only relevant for the blue classrooms. So let me change the color of the error term. So this is already much better. When is our hope that this average is zero justified? Well, we're averaging over values in our sample, so we have to ask where our sample is coming from. We think of our sample as coming from a large collection of classrooms that is called the population. The population contains all the classrooms that we think follow the same economic rules of knowledge production. For example, this could be all the classrooms in the same country or in the same educational system. We collect our sample by selecting classrooms from the population, and most of the time we do so randomly. So this is called random sampling. Let's assume that we sample 1, 2, up to n classrooms. We observe these classrooms and can record their values of test score, class size, and PD index. This is data that we can save, for example, in an Excel sheet. Under what circumstances can we expect averages on the sample to be equal, for example, to 0? The law of large numbers from statistics says that population averages are close to sample averages, at least if the sample size n is large. For the law of large numbers to hold, it's also important that we sample randomly. We can have a reasonable expectation that the sample average is close to 0 if the corresponding population average is close to 0. Population averages can be written as expectations. We'll explain why at a later point. So the corresponding population average can be written as the expectation of the error term in the subpopulation of classrooms that have a class size equal to 36 and face a PD index equal to 20. Let's assume that this population average is equal to 0. By the law of large numbers, the sample average inherits this 0 from the population average. This seems like a good assumption now, but as you'll see in a second, we need something a little bit more general. So for now, let's assume that it doesn't hold for this subpopulation, but for all subpopulations. It holds for arbitrary lowercase d and arbitrary lowercase x. Later, we will call this kind of assumption an exogeneity assumption. Another good name for it would be a balancing assumption, because it assumes that the error terms in the subpopulations are well balanced in the sense that they average out to 0. Previously, we estimated the treatment effect using a single blue classroom and its observed learning outcome. Now we're going to modify this identification strategy. Instead of using a single classroom, we're using an average over classrooms. The average sums over all suitable candidates, takes the observed test score, and then we divide by the number of observations. Before we can discuss whether our estimation strategy based on this quantity actually works, we have to think about how to interpret causal effects now that we have an error term. When we consider a ceteris paribus change, what happens to the error term? What is the error term anyway in economic terms? For every given classroom, U describes the effect of factors other than D and X that are present in the classroom and that affect knowledge production in that classroom. For example, if a class has a particularly clever student, that would enter through U. We said U is like random noise, but that's not very helpful for understanding U economically. For every given classroom, U is not random at all. It's just one facet that describes the circumstances in the classroom. Random noise just means when we compare these circumstances between classrooms, they seem random. When we think about a ceteris paribus change, we're only changing D. We're not changing X, and we're not changing U. What does this mean for our treatment effect? The treatment effect compares the outcome in the counterfactual world to the actually observed outcome. We can now plug in our model for the potential outcomes. So we have m of d plus 1 and x plus our error term u. And now we're subtracting this part minus, there's m, this time evaluated at d and x, plus the error term. The error term shows up here and here, so we'll just cancel. And we're left with the difference between these m functions. This is the treatment effect that we're trying to estimate. Now let's move on to treatment effect estimation. Let's start by considering what y bar is under our model assumptions. Y bar is the average over all the blue classrooms. So y goes from 1 to the blue n, and we're dividing this sum by the blue n. So this will be the average over, and now I'm plugging in the model here. First we have the m function evaluated at the treatment and the confounder plus the error term. Now we've chosen the blue classrooms so that the treatment is always 36 and the confounder is always 20. Therefore, this is a fixed number and we'll just shift the average by this amount. We can move this outside of the average and here get rid of the parentheses. Now this here will be approximately 0 by the law of large numbers. Therefore, the whole thing will be approximately the m function at 36 and 20. Previously, we estimated the treatment effect by the difference between the blue classroom and the purple classroom. Now, our plan was to modify this identification strategy by replacing the single classroom by the average of classrooms here. What will this get us? Well, this will get us approximately m at 3620 minus, and now I'm plugging in the model for this y, the m at 3520 plus the error term in the purple classroom. This doesn't give us the treatment effect that we figured out here, because we end up with this additional error term. How do we get rid of the error term? Well, the same way that we got rid of the error term for the blue classrooms. instead of using a single control classroom, we're using an average of several control classrooms that have similar level of classroom size and confounder. Suppose that we can find purple n such classrooms. We can define a similar average as we had here, and then apply very similar arguments to show that this is equal to the m function, but this time at 35, the smaller class size, and confounder level 20, plus an average of error terms. This again will be close to 0 by the law of large numbers. Therefore, this will be approximately equal to m at 35, 20. Now we can replace the single classroom by this average. We'll get rid of this u. Now we have this difference of m functions. And just to be clear, the first m function is evaluated at purple d plus 1 and confounded level equal to what we see in the purple classroom. And then the second m function is at d, comma, x. This is exactly the expression that we figured out for the treatment effect. Finally, we have figured out a viable identification strategy. Our estimate is close to the thing that we're trying to estimate. Let's take this identification strategy to the data. First, we need all the purple classrooms, that is, the control classrooms. They have a class size of 35 and a PD index of 20. Here we go. We also need all the blue classrooms, that is the treated classrooms. They have a class size of 36 and also a PD index of 20. So now we have all the data that we need to compute our treatment effect estimate. I'll leave the computation up to you. Before I finish this video, I want to point out two issues with our estimation strategy here. The first issue is, what if we have an additional confounder? Maybe let's call it x2. Where is the effect of x2 modeled in this model? Well, it's not here, so it's got to be here. So the confounder x2 would enter the model through u. But we've assumed that u is balanced in the sense of satisfying this exogeneity assumption. Now the effect of confounders is typically not balanced, so in this case we would have trouble justifying the assumption. Of course, what we can do, if we observe x2 at least, is add x2 as an additional term in this m function. In this case we say that we control for x2. However, this may lead to additional complications. But let's first talk about issue 2. Our argument relied on the law of large numbers. We need population averages to be reflected in sample averages. This works only if n is large, that is, if we are taking a sample average over many values. Here we are taking averages over only very few observations. For our control group we have 1, 2, 3 observations, and for the treatment group we have 4 observations. These numbers are way too small to ensure that the law of large numbers works. Now think back to issue 1. If we define the control and treatment groups even more narrowly by requiring that they not only share the same PD index, but also the value of an additional confounder, we make these groups even smaller and take averages over even fewer observations. This picture is a great illustration of our problem. We initially start out with a lot of data, but end up using only a small fraction of it. We're using observations located here for our treatment group and observations located here for our control group. All other observations are ignored. The problem becomes even more severe if we want to control for more confounders. then the treatment and control groups will become even smaller. Adding in an additional control is like adding in another dimension that we want to model. And the problem that modeling more dimensions is hard in terms of diminishing the size of the sample that you can actually use is called curse of dimensionality. If we want to move forward, we have to overcome the curse of dimensionality. But that's a topic for another video. Thanks for watching.